Hello, everyone. I'm Wei Shi from Zhejiang University. I'm glad to introduce our work DAFID, Mobile IoT Communication, Exploiting Stealthy-Speaker-to-Gyroscope Channel. This is a joint work conducted by Zhejiang University and the State University of New York at Buffalo. IoT has been widely deployed in real-world applications. It is expected that every device can freely communicate with others in IoT. But there are still many obstacles to realize such an everything-connected IoT network. We illustrate the problem with two robots. An old robot Rowe meets with an up-to-date robot Eve. Rowe may just support several protocols due to its old age. For example, Zigbee or Bluetooth Low Energy, with the purpose of power saving. Well, Eve may support different protocols like Wi-Fi, Bluetooth, or in Ocean. Even worse, manufacturers develop their own protocols. For example, Google, Amazon, and Huawei. In this case, Rowe is likely to only support private protocol developed by its manufacturer. In this case, those incompatible protocols prevent them from chatting with each other. In another case, they might share a compatible protocol for communications, but the electromagnetic interference or sharding is catastrophic for communications. They are also hidden from talking to each other. In addition, current wireless communication always requires necessary pairing between the transmitter and the receiver. Considering Rowe is too old, it's out of order both in hardware and software. It's like Rowe is deaf, so he fails to hear what Eve said. Our version here is to establish a protocol-independent channel. It requires no additional hardware and can be adopted in most current IoT devices. Moreover, it is significant to ensure the robustness of communication channel in a mobilizable IoT network. In short, it enables the deaf device to hear what others are saying. We turn our attention to gyroscope. Interestingly, we found that it will respond to ultrasound and produce low-frequency readings. With this observation, it is possible to build a complementary communication channel to current IoT devices. So, if using such a system, we can aid the deaf Rowe to understand what Eve is saying. To confirm the feasibility of our version, we test on 8 models of gyroscopes to study its response to ultrasound. Their resonant frequency bands are beyond the range of human hearing and always ignored by the speech recognition system. But they all show a well response to certain frequencies in the ultrasound spectrum. Thus, we are confident that such a non-content speaker-to-gyroscope channel is feasible to set up with commodity speakers. Before the introduction of the system design, let us have a look at the principle of the resonance and the process of data transmission from a speaker to a gyroscope. Gyroscopes have become a common part in intelligent devices, including smartphones, VR sites, wearables, wearable devices, remote control devices, and the like. Due to the special structure of gyroscopes, the acoustic inputs of specific frequency bring resonance on a gyroscope. We set the input frequency as F0. We follow the plus interval encoding, PIE. Well, a short interval delta t indicates 1 and a long one implies 0. And as a result, the frequency of resulting oscillation in the gyroscope keeps F0. Resonance introduces a gain coefficient and a phase difference. They are determined by the frequency radio of F0 with Fn. Typical MEMS architecture in a gyroscope, which comprises three parts: amplifier, filter, and analog to digital conversion. The former two introduces a fixed and insignificant deviation. And during the analog to digital conversion, the frequency of input is usually higher than the sampling rate. This leads to aliasing. Finally, we obtain a low-frequency output. Its frequency F1 is decided by the input frequency F0 and the sampling rate. Finally, as the receiver can know delta t by observing the appearance of F0. In this way, signals are received by a gyroscope. We are confident that Def8 can be applied widely among various IoT devices. However, to build a high-quality and robust channel in a mobile IoT network, we have to address several challenges. Firstly, because IoT devices are mass-produced, and it is difficult to identify them automatically if you just want to send information to a given device rather than broadcast. So, how to identify the receiver is a key issue, especially in a dynamic IoT network. This means we must guarantee that the receiver is void when Eve shares secrets with him. Traditional methods require excessive configurations or manual identification, which are impractical here. We propose a new device fingerprint, the ID range, to help Eve to identify word E from other devices. It is extracted from the diversity of resident passband of gyroscope at word E. To verify the stability of this feature, we prepared an experiment on 6 speakers and 12 chips for its validity. Our experiments show that jointly using them to generate a device fingerprint will lead to a 96% accuracy in identifying the receivers. Secondly, low error rate is the basis of good communication. The basic general principle of communication is to ensure a high quality with as little as possible noise. However, because of gyroscope inherent noise, word E may misdecode what Eve sends. Traditional anti-noise technologies are usually based on spectrum analysis, but the impact of noise is still significant because of the random and unpredictable frequency offset. It is caused by the sampling rate drift of gyroscope. Since the output frequency depends on the input frequency and the sampling rate, even if the input keeps stable, slight changes in the sampling rate may cause a remarkable frequency offset. Previous solutions focused on the resonant data on individual axes and neglected the relation among multiple axes. We observe that all axes share a same response frequency and follow a fixed phase difference. Thus, if we leverage this stable parameter to correct the offset, we can improve the accuracy in the decoding. So, our idea here is to apply a multiplier. The result includes a constant, a second harmonic component, and high-frequency noise. The latter two can be removed by a filter. In this way, the constant would be invariable value for the correction, and we thus obtain an error-free channel with a high signal-to-noise ratio. Here, we provide an example of transmission. A speaker plays the modulated ultrasonic signals. We define different time gap ones between the racing edges of the pulses, where a short interval indicates 1 and a long one implies 0. A gyroscope responses correspondingly, and the noise is removed in aforementioned way. We employ the maximum entropy threshold method to decide the threshold, and then found the racing edges larger than threshold to encode. In this way, the information can be correctly decoded from the received signals in gyroscope. In addition, DAF8 supports multi-channel communication. We observe that there are two frequency bands, where two axes resonant mean well. It is often the case that the spacecraft may give a command to Rowe when she is chatting with Eve. In this case, Rowe can leverage the those multi-channels, so he can follow the orders from the spacecraft and listen to Eve at the same time. That is, DAF8 supports parallel communications on multiple channels, even from two transmitters. Last but not least, motion inference is a key issue. It is necessary to suppress its influence in case of the additional reading and error during the communication. We consider three sample forms of movement: transmitter moving, blocking in the line of sight, and the receiver moving. In reality, if some object moves onto the line of sight between Rowe and Eve, it will generate a sudden error, and as a result, the information would miss such that Rowe fails to understand what Eve is trying to say. We utilize interleaving technology to reduce these burst errors. It changes the information structure to the greatest extent without content alternation. Given the line of sight is blocked, the decoder can treat these errors as random ones. In this way, the error brought by the blocking can be dispersed and minimize its impact. The other issue is light. The transmitter's motions lead to variations to the transmission distance. It results in signal fluctuations. Simply using a global threshold cannot deal with these fluctuations well. If it is too high, the message would be lost. Well, if it is too low, noise may be recognized as characters. Inspired by the idea of a threshold window, we realize adaptive threshold for calculating the value of threshold within a short-time segmentation. In this way, the threshold can be timely adjusted to effectively mitigate the fluctuations, so that Rowe understands what Eve said. On the other hand, movements of the receiver itself also forces the gyroscope to produce additional readings. For example, in this case, when Eve calls Rowe is moving. The Rowe's gyroscope produces additional readings, and the communication channels would be ruined. So he couldn't make out what Eve is saying. To deal with this issue, we adopt a BSS model and reorganize components based on inter-axis characters. DAF8 manages to be robust against movements in a mobile network. Then, we build the prototype of DAF8 using off-the-shelf gyroscopes, speakers, and phones. For evaluating transmission capacity, we test on gyroscopes with different parameters. It can reach 47 bps, while BER remains a low level within 0.6%. It is competent for the different requirements of transmission speed and tolerance of error flexibly in various occasions. For evaluating performance in different orientation, we rotated a 5-watt speaker around the gyroscope. The results of SNR and BER keep similar in all directions, which indicates the flexibility on the placement. For evaluating the communication distance, we raise the power of speaker to 30 watts. It can reach up to 40 meters. Similarly, we repeat these experiments using the gyroscopes encapsulated in the smartphones, including Galaxy S8, Pixel 4, and Mi 5 Plus. We rotate the speaker around the fixed phone, as their screen is set vertical and parallel respectively. It can still retrieve messages sent word depth, no matter in which orientation it is. And it keeps communication with those phones up to 12 meters away. The gyroscope encapsulated in Pixel 4 shows the shortest communication distance, 4.4 meters. But it is still satisfactory in many scenarios, such as the indoor environment. To evaluate the robustness of prototypes, we organize volunteers in pairs. One volunteer holds a speaker and the other carries a gyroscope chips or a smartphone. Both of them move within a range of 2 meters randomly. As a result, the mean of BER is below 1%, and the peak is lower than 7% during the entire experiment. This indicates the depth facilitates a robust channel among mobilizable IoT devices in a real-world implementation. There are various other physical phenomena which can be leveraged for data transmission among devices. For example, vibration, heat, and sound. They succeed in building a communication channel in some scenarios. Compared with them, depth is flexible, accurate, and robust. It enables IoT devices to identify and chat via labels remotely without the reconstructions of additional hardware content and fixed placement in a mobile network. To implement depth in reality, we take the power consumption into consideration. Currently, in the audio components of IoT devices, the power is almost consumed by the speaker. We obtain the communication distance of 20 meters from a 5-watt speaker. We adopt such a setting with the consideration that some IoT devices are equipped with such a power-limited speaker for the purpose of low power consumption. For those devices with less strict requirements on power consumption, the communication distance can dramatically increase, and the distance can be extended up to 40 meters. A better speaker could further extend the communication range. It is reported that ultrasound is capable to affect gyroscopes 37 meters away. We also exploit the potential of depth from a security perspective. Both auto may jam the communication between VE and EVE, but it is difficult to find out the appropriate band. It has to jam in a broadband spectrum, but EVE can detect the jamming in time with a microphone easily. Depth can also prevent replay attacks, even if the private key is leaked. EVE can send a non-informative ultrasound signal, which can also broadcast at a nearby frequency to confuse attacks. It is difficult for attacks to pick out the right one from those false information. In summary, we build a protocol-independent and robust channel for the mobile IoT network, analyze the gyroscope's inter-axis relationship, and propose a novel device fingerprint. Thank you very much. And if you have any questions, feel free to contact us.